We are going to discuss metrology and inspection. So in GATE, there has been a slight change in the syllabus of metrology inspection. They have removed gauge design, that means go and no go gauge designs, and they have added this CMM, that is coordinate measuring machine. So what we'll do is that we'll not discuss the gauge design, and we'll be discussing the coordinate measuring machine, that is CMM. Okay. So coming to introduction of metrology. So what is metrology? Metrology is the science of measurement, precision, and accuracy. Okay. So can anyone say what is the difference between precision and accuracy? Anyone? Anyone in the group can say what is the difference between precision and accuracy? Okay. Precision is related to number of decimal places, and accuracy talks about closeness to the actual value. You are right, but precision is not exactly the decimal number to the decimal value. But what Rahul said, accuracy is right. Precision is little different. Is having a different definition. What I can see. So let others also type, because people are typing here. I see some Murli, Abhishek, and Rahman. These people are typing here. This Ravindra, accuracy is closeness of agreement between true and measured value. That's true. Okay. And what about others? People are trying. Let me wait. Yes. There's so many responses that are happening today. I'm very happy. Precision, smaller least count. Okay, that's okay. And precision is to get the same result by repeat. Yes, precision is right, Murli. So precision is to get the same result again and again. So precision is instead of measuring device. Okay, fine. Anyways, I got some good answers here. Uh, Thank you all guys, Rahul, Ravindra, Abhishek, Murli, and all. So fine. So I mean, already it is here. When in the slide you can see here. So measurement is the method of comparing quantitatively an unknown value with a predefined standard. So everything has to be having some standard. How do you know if you are this many centimeters until unless you have standard of centimeter? So, do you know the actually? I mean, let me go back and tell you some story about this. Robber, not robber. I mean, the accusation of robbery. It was, I think, in during the days of this Sri Krishna Devaraya. You know this guy, this Sri Krishna Devaraya. I mean, he's is very popular in the South India. So there was this guy called Tenali Ramakrishna. I think if you might have heard of him. He's very intelligent guy. Okay, what happened? So initially there was no proper standard, predefined standard for anything in the olden days. Later on, all these standards have come. ISO, all these things. So many standards have come. So how these standards have come? Because let me say there was a story. Actually, what happened in the court of the Sri Krishna Devaraya? What happened? There was some robbery that had happened. So the everyone was summoned upon, and there was a huge discussion going on. So the people accused one guy of robbery. So he is working in the as some vegetable seller. So he was accused that, like, okay, you are the guy who have robbed the gold and all. So now, as he was called upon to the court, and he was like summoned, and he was the people standing there in the court. They were asking that, like, why did you do, and where did you put the gold and all. So now what happened? Sri Krishna Devaraya told that, okay, you do one thing. If at all you're telling the truth, and if you show where you have hidden the gold, then I'll be leaving you aside, or else if you're telling lie, I'll be killing you. So then that poor little fruit, I mean vegetable seller got scared, and he told that, okay, I'm sorry, my lord, I am the robber, and I have hidden that thing in so and so place. So the court guys, I mean, the king has asked that, okay, where did you hide it? So this guy says that you go from the gate of our court, you go straight, take 50 steps, then take a left turn and 20 steps, and then from there you take a right turn of 50 steps. Then you'll be getting. I have dug that gold into the ground. So he told that he has. This is the steps: 50 steps straight, left 20, and right 50. So what happened? This king has sent few soldiers to bring the gold. So soldiers followed the same, uh, you know, directions of this vegetable seller, the robber. So, but the gold was not found. By any chance, do you know why the gold was not found? Even though they are following the same, this thing. Yes, obviously, the steps are different. This small, poor vegetable seller is very short, and his footsteps are very small. The soldiers are very big in height, so they have a big, long steps. So they have missed or spot. They have bypassed the spot because 50 steps already they have bypassed, and then 20 steps left. So they have bypassed the gold. So then soldiers have come back to the court, and they told that, no, no, my lord, we haven't found the gold. Then Sri Krishna Devaraya got so much aggressive and angry. He told that, I'm gonna kill you. So they told that, hang him. But again, this guy pleaded, sir, I'm literally sure that I have placed that there. Please come with me. I'll show you. So when this guy has went, they found out because they followed the steps of the vegetable. So from there, the unit of length 1 centimeters. If it would have been told by a vegetable seller that, like, okay, go 10 meters straight, left 20 meters, and then 10 meters right, then it would have been perfect. So this is how the people have started defining some standards, so that, like, from that standard I can be measuring whatever the component I'm trying to manufacture. So let's come back here. So the precision represents the degree of repetitiveness. How, let's say, if you're doing, let's say, if your diameter of shaft, you are doing a turning, so you want to reduce your shaft to 30 centimeters of diameter, okay? And if at all you are producing 30.08 is the diameter of the shaft that you're trying to produce. If you're repeating the same value again and again, again and again, again and again, approximately same value, then it is called precision, right? So it is degree of repetitiveness. So how many times you are trying to repeat the same value is called precision. And accuracy is how close you are to your true value. Let's say if you are let's say if your original value was to be 30. So in first turning operation you found out 30.1, and second turning operation you found 30.05, and third turning operation you found 30.15, and fourth turning operation you found 30.01. So this is your accurate product. Fourth one is your accurate product because it is very close to your original value, right? But precision is nothing but it's like 30.1 first case, second case is your 30.1, third case is your 30.02, and fourth case your 30.05. So this is your precision because you are maintaining approximately the same value, but yet it is not close close to it. Okay, so that is what is the difference between the precision and the accuracy. Okay, fine. So dimensional metrology is the branch of metrology which deals with measurement of dimensions of parts or workpieces. So that are lengths, angles, and etc. 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 And dimensional measurement at the required level of accuracy are essential link between designer's intent and the delivered product. So Everything is important because designer, when he is designing something, when you're doing the strength of material, so why you're reading this strength of materials, fluid mechanics, theory of machines and all, because you're sizing the material. You size the strength of materials. What you're trying to calculate? You're trying to calculate length, width, radius, and all these components, right? So you're trying to, in machine design also, you're trying to size the material. So designer says that, like, okay, my diameter of bolt should be so and so, my diameter of nut should be so and so. Okay, the shaft dimension should be so. Length is this much, diameter is this much. So designer intent is different, and to make the exact delivery, what you do, you have to produce precisely and accurately. And how do you know whether you have produced it? So you have to have a proper measuring equipment, right? So you have to measure it properly. So the width, the depth, and the angles, and even though you have produced it rightly, if your measuring equipment is wrong, there's no point in producing it rightly, because you, let's say if you have produced it rightly, let's say if you want to produce 30 diameter, you have exactly produced 30 diameter, but if your measuring equipment is wrong and it is showing some 30.8, then you feel that, like, okay, this is out of the range, you'll discard it. So in the first place, your measuring equipment should be perfect. Okay. The width, the depth, the angles, and other dimensions all must be produced and measured accurately for machine tool to function as expected. Okay, so it evolves the metrology and or the industrial. Actually, we are discussing here industrial inspection. Actually, okay, involves inspection of components produced from, like, production, right? Like you are producing this all this from production unit, and you're trying to measure it. Okay, so there are two different type of inspections. The inspection is divided into two different types. One is active inspection and another is passive inspection. One is active inspection and another is passive inspection. So what do you mean by this active inspection? In active inspection, parts are checked when it is being produced in the system. So already the system, the production is being on run, and then you are trying to produce online. It's called online inspection. Sometimes active inspection is also known as online inspection. Fine. And if something goes wrong, then they'll stop the machine. Then the preventive measure or corrective measure has been taking place of, and then start the machining. But in passive inspection, parts are checked when it is already produced. I mean, after the production is done, then they take the goods out, then try to measure with the measuring equipment. That is what is called passive inspection. Okay, fine. So actually, I want to discuss one more point here. The parts which are produced from any manufacturing system, okay, follow a distribution called normal distribution. Have you probability is done in your mathematics course? Probability and statistics. So yes. So what is this normal distribution? It's a simple bell curve kind of stuff like this. So we have discussed this in industrial engineering also. Hope you remember this. Yes. So this is your mean here. This it's called mean, and it's denoted by x bar sometimes, or it's also denoted by mu sometimes. And this is having mean, and whatever is that you're trying to make here, or your standard deviations here. Like this is your standard deviation. So we can write this as 3 sigma here, this side, and this side you can write as 3 sigma on the right hand side. Sigma is your standard deviation. Okay, so machine environment, whatever is there, is considered as infinite universe. Like the machine environment what you have is considered as some kind of universe which is infinite. So machine components that are considered as some random data. Okay, because everywhere so many parts are being produced, some thousand lakhs of parts are being produced, and each and every part is different. No, each part will be same. Every part is different, right? So that's the reason why all this, what you say, the manufacturing system, what I say, follows a normal distribution. So this is called normal distribution. Manufacturing system follows normal distribution. Okay, fine. So again, we are going back to this precision and the accuracy, or accuracy and precision. Accuracy is defined as closeness to the exact value, and precision is repeatability. Let's go and draw one graph, and okay, let me take this in. So let's say this is your y-axis and this is your x-axis, and let's say this is your frequency. Frequency in the sense like how many components you are trying to manufacture here. This is your frequency of your machine, and then this is your dimension. Dimension. So let me draw this graph. If your distribution is something like this, then what is this? So let's say this is your mean value. This is your mean value, and the targeted value, the original value was supposed to be somewhere here. This is your targeted value. See here, the mean value of the observation is very close to the target value, but there are large fluctuations in the observation due to higher process capability. Such systems are accurate but not precise because you're not producing the values similar, like what you say, the spread of the standard deviation is very high. The spread of the standard deviation is very high means it means that it is not precise but yet it is accurate because your mean value and targeted value are almost near, because these two are almost near, hence it is. This one is this diagram especially is accurate but not precise. Accurate, sorry, ACC, right, but not precise. Okay, and on the other hand, let me draw the diagram of another thing. If you see, this is having less spread and have some mean value, and you have targeted value. So this is what, this is having less spread, so more precise, and also the mean value is near to the targeted value. The standard deviation observation is low, and also mean is close to the target value. So the systems are precise and accurate. So accurate and precise. So going to the next slide, you can see the diagram. So let me draw in the same ink now. I don't want to change the pen every time. So this, so spread is less. This is your mean value, mean, and the target is somewhere else. So what is this? This is precise because the standard deviation is less, but it is not accurate. So precise but not accurate. So if we take another diagram here, this is a big spread. This is your mean value, and targeted values are somewhere else. So this is neither precise nor target, nor accurate, not target nor accurate. Okay. So, and now after, let's, after coming after, I mean, after knowing some basic terminologies like accuracy and precision and about little bit of measurement and all, let's go and start our major discussion, that is your limits, fits and tolerances. So as I told you that, like, the why there are different parts, how why each and every part is different from each other. Anyone can say why not even a single part is close to each other part? How, why is it a problem? Yes, manufacturing, it can be manufacturing, it can be process capabilities. So it's so many other different wide variety, lot of uncertainties is right. Manufacturing is also right. Tolerances, we are providing the tolerances. We are providing the tolerances because of this manufacturer, because of this process incapabilities. Good, 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 excellent. So fine. So let's discuss. So it is impossible to manufacture any product precisely to a given dimension, even if by chance the product is exact. That's what I told. It is impossible to measure it accurately to prove it. That is a problem. Even though it is right, you are having some problem with your equipment, so you can't prove it. Right? If attempts are made to achieve perfect size, the cost of production will be increasing tremendously. You feel that like very small, minute change, 0.00001 micrometer is less than gone. You have to have a high, precise, and accurate instrument to measure the money will be searching like hell. Okay. Uh, Therefore, some permissible variation has to be allowed. That's the reason why limits, tolerances, and limits and tolerances will be coming to picture. So, what is the definition of limit? So, limit is nothing but the permissible sizes, that is maximum and minimum, within which the size of the component lies, are known as limits. It is classified as upper limit and lower limit, right? So now initially what I told, like for example, I told you that if you have to produce 30 of diameter, then what you do, you say that like no, you can't produce this because of this 3 points I told you. It is having some manufacturing problem, and you can't prove it even they're doing to trying to manufacture it properly. Or if you want to achieve a high level of accuracy and precision, the cost is going up, so you don't want to happen that. So that's the reason why you're putting this limits. So the limit says that okay, I don't want exact 30. It can lie between 29.9 to it can lie and it can go up till 30.1. So he says the production or the drawing says that the limit can be lying between 29.9, like your gate answer. When you're writing a numerical type answer, it is having some kind of range, no? Because everybody is not same. Everybody's calculation is not same. Somebody will keep do the calculation till 3 decimals. Somebody will take 2 decimals. Somebody will take 5 decimals. The more the decimals, more the time, more the accuracy you'll get. That's the reason why gate will do that. This kind of range. So if you get in this range, then you're right. Similar way, if you are having this range, and this range, this is called your upper limit UL, and this is called your lower limit LL. This is your upper limit and that is the lower limit. So these are the limits. And what is tolerance? Tolerance is the permissible variable in size or dimension. So tolerance is nothing but the permissible variation. How much is the variation here? From 30, it is 0.1, it is going up, and from 30, it is coming 0.1 down. So that is the permissible variation. So it's a difference between the maximum limit and the minimum limit. So the tolerance here is, let's say, here in the above case will be 30.1 is your upper limit minus 29.9 is the lower limit. So the tolerance is 0.2 here. Got the point, sir? Okay, good, good. Okay. The plus minus sign. Okay, yeah, that is what is limit, but we haven't entered into that, so we have to exactly do that. Fine. So let me discuss some more extra points in tolerances. So the tolerance is total amount of dimension may vary, and it is the difference between, okay, there is a gap here. It is the difference between the upper or maximum and lower or minimum limits. There are two different type of tolerances. The tolerances are dimensional tolerances and the geometrical tolerances. So the allowance for a specific variation in the size of part is called dimensional tolerances. It means that in the size of the part, in the number, that is 30, 31, 29.9, 28, 31, 30.1. So these are the variations that you are trying to put onto the size of the part, then it is called dimensional tolerance. And allowance for a specific variation in the geometry of the part. Geometry in the sense like It can be cuboid sometimes, then it can slant, then it can become a parallelepiped. So that is called geometrical tolerances. So but here we are discussing the dimensional tolerances. Okay, so tolerances are used to control the amount of variation inherent in all manufactured parts. One of the great advantages of using tolerances is that it allows for interchangeably parts, that's permitting the placement of individual parts. What is this interchangeability? Can anyone say this interchangeability? Because shafts are manufactured somewhere and holes are manufactured somewhere. Holes in the sense like some nut or some place where hole is required, some for somewhere hole is being manufactured and somewhere shaft is being manufactured. These are thousand number of items and these are like some thousand number of items. So let's say if you're not having if you're not having tolerance, so what happened? You have to identify the shaft of diameter 30 and you have to identify the diameter of 30, then only the shaft can go into this hole, right? But if you're keeping the tolerances, there's some tolerance limit like 29.9 and 30, sorry 30.1 and 29.9. So if you do the, so almost all the shafts can go into almost all the holes. Any shaft can be picked up and any into put into the any of the hole. Okay, so that is the reason why this is called the interchangeability. So you can keep any shaft into the any hole. That's called interchangeable parts. Interchangeability it is called. Okay, fine. So there are differences. That is your unilateral, the what do you say, tolerance representation and the bilateral tolerance representation. You can see here in the examples here itself. You can see unilateral in the sense you have one of the limit 0 only on one side of the limit. It is, you can see here. See the length was supposed to be 22, but the upper limit is 0 and it can't go up. You can't increase the dimension of this part, not even with 0.0001. You can reduce the dimension of part with 0.0.3. It means that it can go till 21.7. So the tolerance is 0.3 here and the upper limit is 0. And if you see here, I mean, if you see onto this side, this is also a unilateral tolerance. That is like if you see the upper, it can go up till 12.1, but it can't come below 12 is the maximum limit and it can't come below 12. And angle also you can see 25.6 will be the angle, and upper limit it can't go up, lower limit it can come down, so it can come to 25.4 degrees. So this on the left hand side is called unilateral tolerance because dimensions of the part is allowed only one set of basic size. So basic size is this 22. 12 is the basic size. 25.6 is the basic size. In bilateral tolerances, the dimension of the part is allowed on both the sides of basic size. It means that you can see 22 plus or minus 0.2. It means that it can come down 0.5, 0.2 units and it can go up 0.2 units. And if you go to this thing again, here it is 20.22, it can go up 0.1 unit and come down for 0.2 units. And also here is a bilateral one, here also plus or minus 0.5, 0 degrees 5 minutes. So angles are measured in degrees, minutes and seconds. Okay, so 0.0 degrees and 5 seconds. So these are on the right hand side, you can see these are called bilateral tolerances. You got the point, sir? So this is the difference between unilateral tolerance and the bilateral tolerance. Let's see some important terminologies in tolerancing. So because we are discussing about tolerancing, how much you have to keep the tolerance. That is tolerances, please remember again I'm saying upper limit, lower limit. The difference between upper and lower limit is called tolerance. Please remember that. And we can have two different type of tolerances, that is unilateral and bilateral. That is what we have discussed. Fine. So next, so let's discuss some basic terminologies and let's jump into some formulations. Okay, see here, I mean, I'll come to this picture after discussing all the terminologies. Okay, shaft is nothing but a term used by convention to designate all external features of part, including those which are not cylindrical. Please don't assume that shaft means only diameter. which is not cylindrical also, you can assume it to be a shaft, because here we are thinking that hole and shaft system, because we assume that this is a fitting system, right? So even though it is not cylindrical, it is designated as shaft. So shaft doesn't mean a pure shaft, exact shaft, but all the external dimensions of any part is called a shaft. No, shaft is not a shaft. You are right. Okay, a hole, a term used by convention to designate features of part, including those which are not cylindrical. Okay, so this is called a hole. Okay, fine. Basic size. So basic size in the sense like what the designer has intended to have. So the nominal diameter of the shaft or bolt or hole, this is in general the same of for the both components. So basic size you see here is 22, 22, 22, 12, 26.5, 26.15. The external features on the sense like wherever like external thing, external in the sense what, like here in the shaft the outer diameter is the external feature, the whole internal diameter is the internal feature. That is what is the external and internal features. Okay, yeah. So the nominal diameter you have seen, it's a simple designer intended. He wants the 30 diameter, 30 mm diameter. That is the basic size. That is what the designer has intended to have. What is actual size? Actual size is nothing but the measured size of the finished part of the machining. So after basic size was intended, then what you did, you manufactured it, then you have measured it, you found out the actual size. That is what is the actual size. And zero line. Zero line is nothing but it is a straight line corresponding to the basic size. The deviations are measured from this line. The positive and negative deviations are shown above and below the zero line respectively. So that is what is this basic line. You see here, so this is your zero line here on the here the zero line or line of zero deviation. Zero line is this. Okay. So this zero line means what? Like there is your 30 mm of diameter. Let us go with the same example from right from beginning to the last. So 30 mm of diameter in the sense like you have the zero line starts with the 30. From if it is going up, then it is increasing. If it is going down, then the 30 mm is decreasing. Whatever you are writing below the zero line will be below 30. Whatever you are writing above the zero line will be above 30. That's it. So you see here, so shaft is this and hole is this. So if you see this zero line, from zero line, the shaft is having this upper limit of shaft. You can see this upper limit of the shaft, the upper limit of the shaft, and this is your lower limit of the shaft. Okay, this is your lower limit of the shaft, and this is the lower limit of hole, and this is the upper limit of hole. Okay, so these are the different, and this is your basic size. Whatever the basic size is, this is your basic size. Basic size in the sense like that whatever the manufacturer was intended to have. So don't forget about all this lower deviation, tolerance, upper maximum diameter. Don't much about this. This will be discussing in the coming slides again. Don't worry about it. So this is the zero line. So deviation is nothing. So please remember, this deviation is very important. Deviation is the algebraic differences between actual size and the basic size. Okay, for hole there will be some deviation. For shaft there will be the deviation. Please remember this. It is the algebraic difference between the actual size and the basic size. That is the deviation. Next, upper deviation and lower deviation. Upper deviation, it is the algebraic difference between maximum size and the basic size. Okay, so you see upper deviation, you can see here like maximum size of the shaft is this and the basic line is this. The difference between the maximum limit and the basic limit is your upper deviation, and you can see here maximum size and basic size is upper deviation. Upper deviation of hole is represented by a symbol called ES, and I'll draw the diagram again, don't worry. ES is a cart superior, and of a shaft it is represented as ES. So this is for hole you write in a cap. So please remember from now, if something is written in capital, then it is representing a hole, and something is representing in a small letter, then it is called shaft. Okay, please remember, if some letter is written in capital, then it is corresponding to a hole. If something is written in a small letter. So then it is representing a shaft. Again, lower deviation. It is the algebraic difference between minimum size and the basic size. So the lower deviation is represented by EI, that is inferior, and of a shaft it is E small ei. So you can see here. So the minimum size of shaft is the bottom line here. That is the reason why the zero line is here. So you can see the difference between the basic line and the I mean here it's showing the different value. So it is showing the difference between upper and lower deviation. Means basic line and the minimum value, maximum value is called the what you say. So minimum value and the basic value is called lower deviation. Okay. Please try to understand this all these terminologies. If at all you want to take the screenshot, keep the screenshot ready for the problems that are coming up, because you have to do lots and lots of practice and to make sure that you are ready with these concepts. Fine. So this is what is okay. Here it is very clear about your upper and lower deviations clearly. So if you see here, this is your zero line, that is your basic zero line, and this is your basic size. Basic size is the this is your center line. Let's say if you are taking a shaft, yeah, that's what. Okay, I'll show you that zero line basic size. Okay, see if your shaft is like this. So this is your basic. This is your place where it is shafting, because whatever this line is, this okay, this, because you're not representing the complete. The shaft is like this actually. It is something like this. You're not representing the complete. This thing. This also is tolerance actually. This shaft is completely solid actually. This is completely solid, but you're showing only the tolerances limits. This is your tolerance limits. Okay. So this line what I'm showing is your center line, and from center line you had some intended value. You're designing some value. That is your basic size. Got the point? And on the basic size, this basic size is 30, right? So that is what is called your zero line. Got the point? Yes, sir? No? Yes. Yes. Okay, good. So this is your basic line. I mean the zero line, and the basic size is this. Now shaft is having a upper limit of this much. This is your upper limit UL of shaft, and lower limit of shaft. Okay, shaft can go up till this dimension. It can go up till, let us say this is 30. Shaft can have upper limit of 29 point some, let us say this is some, 29.8, and lower limit of some 29.6, let us assume. And hole can have the lower limit of this is your lower limit of your hole. It can have some 30.1, and upper limit of hole is some 30.02 of size. Okay, so as I told you, the upper deviation is nothing but the maximum size, is the difference between maximum size and the basic size. So the maximum size is the upper size, upper limit, right? So this is your maximum size minus the basic size. Minus the basic size will give you upper deviation. So basic size is this, and maximum size is this. If you are subtracting basic size minus maximum size, you will get the upper deviation. Similarly, if you subtract basic size minus the minimum size, then it will be the lower deviation. This will be the lower deviation. In the same case, here also you can see the difference between the minimum size. So this is your minimum size. So difference between the minimum size and the basic size is your lower deviation, and difference between the maximum size and the basic size is the upper deviation. Okay, sir. Basic size is not the center of shaft. Basic size is this. This is your zero line, and this is your basic size, and this is your zero line. And whatever I'm trying to draw, is your this is your tolerance, like this. Got the point? Yes. Hope everyone got the point here. What I'm trying to discuss. So sometimes instead of like here you got the point clear. So this is and there is one more thing that I want to discuss here. So I didn't write all this the um, ESE, I know. So obviously you can write here. So let's say this is some basic size. This is some basic size, and you have some whole system which is having some tolerance of this. Whole system is tolerance of this, and this is EI, that is a lower limit, and this is ES, upper limit. And as I am writing capital, it represents whole. So this is what is called your width of tolerance. Width of tolerance. This upper limit minus lower limit is tolerance. Width of tolerance zone, and how much it is, how much the whatever the variation is happening from the basic size. So this is called your fundamental deviation. Let me write a different thing. So don't worry, we'll discuss that fundamental deviation, but as of now, you remember this is your fundamental deviation. So this is your fundamental deviation. Okay, guys, got the point? Any doubt in this till now? Because it's very important. Got the point? So if you see for whole, this is your fundamental deviation, and for shaft, this is your fundamental deviation. Yes, basic size theoretically exact size. You're right. Basic size is theoretically exact size. What's ES and EI again? ES is your limiting, which is representing the upper deviation, and EI is representing the lower deviation. Okay, guys. Yeah. Okay. So this is your basic, like the fundamental deviation. Okay, I write here itself because I've written it. So the distance from the basic size where the tolerance zone is suited is called fundamental deviation. Okay, fine. Got the point. Good, excellent. Let's go. It's a very nice metrology inspection is very interesting actually. Okay, fine. Okay, now it is hole and shaft basis system. So there are two different systems that we are going to discuss from here. That is your hole basis system and a shaft basis system. Hole basis system is nothing but, okay, then it is ICA. Then it is ICA, and then it's ICA whatever superior, and ICA inferior, whatever it is. I'm also not sure it is a French word or not, but I got it from some notes. That's the reason I have written it, because people write it EIES, so people will confuse like why it is ES and ES. Again, see, even Abhishek also got what's ES and EI when he wrote. So please don't get confused. Confusion. Okay, yeah, so it is shaft whole base system in the sense. So the lower limit of hole is directed to the zero line. It means that lower limit is zero and the upper limit is something else of the hole. So this is called the hole based system. So this is called hole basis system. In an assembly, H type of hole appears, then it is system is called hole basis system. Okay, in an assembly, if H type of hole appears, then it is called shaft basis system. So you can see the shaft is directly attached to the, so the what do you say, the upper limit of the shaft, the upper limit of the shaft is directly to the zero line, then it is called shaft basis system. So please try to understand this from the diagram. The basic zero line is touched to the hole. The lower limit of hole is touched to the zero line, then it is hole basis system. The upper limit of the shaft is touched to the zero line, then it is called shaft based system. Okay, hope you understood the point. Let's go and see the variations of different fundamental deviations types. So on the left hand side you can see the hole basis system. On the right hand side you can see the shaft basis system. So on the left hand side hole basis, so each and every hole starts from the zero line. The lower limit of the hole is starting at the zero line, and the shafts are starting from these things. So these are the numbers that you can see in the chart. If you go and see in any of the charts in your tolerances, you can see this. So what are these H8, H7, 7? These are grades, but we are not going to discuss that. We are going to discuss in the coming slides. But as of now, you understand that all the holes are starting on the basic line. On the right hand side, all the shafts are starting onto the basic line. That is what is that you have to importantly remember in this slide. Okay, you can see, if you, I think if you zoom and see here, so this is your hole and this is your hole tolerance here, and I mean this is your shaft tolerance here, whatever it is, the shaft is going up. So what is, so there are different fits, because we haven't come and discussing we haven't discussed the fits yet, so I'm not discussing all these things here clearly. Let's discuss this thing once we are done with the fits. Okay, fine. Let's go to next. So here what we are discussing is fundamental deviation. Already I've told you what is the fundamental deviation. Let's discuss the fundamental deviation again here. It is one of that two deviations, either upper or lower, which is nearest to the zero line for the whole or not. So upper or lower, it doesn't matter, whichever is the near. Here the fundamental deviation is this. Here the fundamental deviation is this. So whichever line of shaft is near to zero line, that is fundamental deviation. Whichever whole line is near to the zero line, that is called fundamental deviation. Okay, this is called fundamental deviation. The upper limit is, okay, same thing. There are 25 fundamental deviations. There are 25 fundamental deviations. See, everything here is in capital letter. As I already told you, a capital letter represents the whole system, holes, and the dimensions of shafts, whatever. Sorry, these are small letters. Okay, holes are like this. Holes are like this. Shafts are like this. So let me redraw that again. So these are holes. H, P, Z. All these things are holes. And if I take different ink here, that is this, these are shafts. H, no, these are shafts. Okay, so why this have been drawn like this and like this, I'll tell you, because that are representing the 1 minute. Yeah, so these are because of the limits that we are going to discuss. So I should have drawn the diagram of fundamental deviation here, but yet I'm drawing it again here. So this is fundamental deviation. Wait 1 minute, I'll draw that. So this is your simple basic line, or zero line you can say, or baseline also they come, zero line. And if you have some some width of tolerance here, and this is called your, this is ES, this is EI, and this is your width of tolerance, and this is your fundamental deviation. So, in the bottom you can see here any information in capital letters represent hole and in small letter represents shaft. Very important point. Value of fundamental deviation for A type hole will be the same as A type shaft with a different sign. So what he's trying to say is that the value of fundamental deviation for A type shaft and A type hole and A type shaft will be equal. Okay, so the distance, whatever the fundamental deviation is here, is equal to the fundamental deviation here with a negative sign. Here it is positive, here it is negative. That's it. That is what is the uh, meaning of the second point here. That is, value of fundamental deviation for A type hole will be same as a small A type shaft with a difference in sign and so on. Okay. Okay, fine. Let's go and see the bilateral tolerances. I told you already, unilateral and bilateral. When the maximum limit is above and the minimum limit is below of the basic size, then it is called bilateral tolerances. I have discussed again. I don't know why I have put the slide again here. If you 1 minute, 1 minute. Huh? Okay. Okay. So what is allowance here? Allowance is nothing but it is a difference between already. I have discussed allowance. No, why I am putting the slide again? Let me see. I think I have discussed allowance, right? No. Okay, fine. Okay. Allowance is the difference between maximum material limit of the hole and the shaft. Depending upon fit, it is equal to the minimum clearance or maximum interference. Okay, that is what allowance is. Okay, fine, fine, fine. Okay, allowance is different. So what he's trying to say here is the it is defined as the difference between maximum material limit. What is the maximum material limit? Maximum limit can be termed as maximum shaft size or minimum hole size. That is what is called maximum material limit. Please remember, this is very important here. Excuse me. Maximum material limit can be termed as maximum shaft size and minimum hole size. Okay, maximum shaft size and minimum hole size. That is what is called your maximum material limit. Why it is called? Can you make the sense? Maximum shaft size and minimum hole size. Maximum material limit. Anyone? Sir, the sign doesn't depend upon the basis selected. What does that basis, Amit? I did not get your point. Yes, material is maximum because if you are having more maximum shaft, maximum diameter is required. For minimum hole, you have to have more material. That's the reason why it is called maximum material limit. So, the difference between the maximum material limit of hole and shaft, depending upon fit, it is equal to the maximum clearance or maximum interference. So, this clearance and interference we'll discuss in the coming slides. So, what is the maximum shaft size? Let's discuss that. So, let's discuss the maximum shaft size. Maximum shaft size is equal to, sorry, maximum shaft size minus, sorry, that is what is this, no, that's what is this, they are discussing the difference between that, minus minimum hole size, minimum hole size is equal to maximum interference. This interference I'll discuss in the coming slides. Please don't worry about this interference and all. and minimum hole size minus maximum shaft size is your clearance, because if there is a positive value here, then it is a minimum clearance. A clearance. Okay, so that's the reason why allowance, you can say allowance is equal to minimum clearance or maximum interference. So this clearance and interference will come from clearance fit and interference fit. So we haven't discussed that, don't worry. I'm writing these points, we come back and discuss this again. Okay. Okay, now that's what we are coming into picture. That is your clearance fit, interference fit, transition fit. So these are the three different fits that we are going to discuss now. So what are the fits here? So it is nothing but, you can see the diagram here, it is very clear. Here the interference and clearance fits are shown, but the transition fit is not shown. In the next coming slides, I will show you the differences. What is a transition fit and all. Fine. So the clearance fit occurs when toleranced mating parts will always leave a space or clearance between when assembled. What is that he is trying to say is that, you see the diagram here, this is shaft and this is hole. So the upper limit of shaft is lesser than the lower limit of hole, and there is some clearance that is provided here. There is some clearance provided. Even though you are getting the shaft value more, even though you are trying to get minimum value of maximum value of shaft and minimum value of hole, then even though you are getting the maximum value of shaft and minimum value of hole, the shaft will be going and fitting inside, and there is a space left between. So that space left between is called clearance, hence it is called clearance fit. Okay, what is interference fit? Interference fit is that interference fit occurs when two toleranced mating parts will always interfere when assembled. Obviously, see, you take the lower limit of shaft and you take the upper limit of hole. uh, what happens, even though you take lower limit of shaft, you're trying to manufacture the lower limit of shaft and you're trying to manufacture upper limit of the hole, the shaft will not go inside the hole. Obviously shaft and hole are not going to fit each other. There is interference between hole and the shaft, that is called interference fit. You are going to ask, sir, how they are going to get fitted? Sorry, if the hole dimension is very small and the shaft dimensions are very high, how they are going to fit? Anyone? Guys, 1 minute. 1 minute. I'll just pause. I got a call actually. You are now unmuted. Okay, guys. Fine. So that is what is interference fit, and transition fit is not. Ah, okay. I asked how you are trying to fit. I didn't get the answer. How you are trying to fit that? Anyone? Yes, it's force fit. Shrink fit is also right. Tight fit also is right. Okay. Shrink fit is the right answer. So in shrink fit, it's also known as heavy force fit, or sometimes you have actually it is called force fit. The heavy force fit is called shrink fit, and there is medium force fit also, and there is a tight force fit also. Okay, so this is how you join no two interference parts. Okay, interfered parts. Okay, so oh, each and everything is clear here. Okay, let me see. A transition fit occurs when tolerance meeting parts will sometimes be an interference fit and sometimes be an clearance. So sometimes it can be an interference fit and sometimes it can be a clearance fit. That's the reason why it's called a transition fit. Okay. So in clearance fit, you can see that the clearance in clearance fit, an air space or clearance exists between the shaft and hole, whatever the tolerances limits that you're taking, whether you're taking upper limits, lower limits, whatever it is, any limit you take, there is some air space or clearance existing between these two shaft and hole, then it is called clearance fit. And such fit gives a loose joint. Obviously, shaft is loose inside the hole. Clearance fit has positive elements, and there is a minimum positive clearance between the higher limit of the shaft and lower limit of the hole. Allow rotation of sliding between the mating parts. Obviously, it can slide, it can rotate also. So clearance is equal to hole minus shaft. Hole minus shaft is greater than zero. Hole is greater than zero. Obviously, hole should be completely greater than the shaft. Okay. Coming to the interference bit, you can see the so you if you want me to make the diagram, you can make the diagram or no need. I mean, you can understand it easily. Okay, let me draw the diagrams because let me let me drink the water and then discuss. Okay, let me draw the diagram for you guys. So if you take a whole basis system, let us assume a whole basis system, and this is whole here because the lower limit of hole is touching the basic line or zero line, and if at all this is your shaft, so this is hole, this is shaft, and this is your maximum clearance. Maximum, sorry, minimum. It's not maximum. It is minimum clearance. So this is what is called your allowance clearance, and this is your maximum clearance. This is your clearance fit. Going to the interference fit. So again, I'll take a. So it is negative difference between diameter of hole and the shaft. It is called interference. In such cases, diameter of shaft is always larger than the hole. It is used for components where motion power has to be transmitted because it has to be tight fit. Interference exists between the high limit of hole and the lower limit of the shaft. Obviously, hole is lesser than the shaft. That is what is your interference fit is. Again, let me take the hole basis system, right? So this is your hole, and shaft will not lie between below it. It will completely lie above because shaft will be bigger than the hole. So this is your shaft, and this is your minimum interference. You can say here. Minimum interference, and this is your maximum interference. Maximum interference. Okay, and this is your zero line, and this is your interference fit. Coming to transition fit, it is between the clearance and interference fits. It may result in either clearance fit or interference fit depending upon the actual value of the individual tolerances of meeting parts. Transition fits are components between clearance and interference fit. They are used for applications where accurate location is important, but either smaller small amount of clearance or interference are permissible. So this is where you are using it. So let me draw the diagram, the simple plain diagram for you. That is, if you're taking the whole system here like this, and now the shaft will be in between like this. So if you take the upper limit of shaft and lower limit of hole, then it will be fitting. If you're taking lower limit of shaft and upper limit of hole, then you cannot fit it, right? Hole, shaft. So this is your zero line. That's it. This is your transition fit. Got the point, sir? Okay, good. Let's go. So let's go and calculate the standard tolerances. Like how do you calculate the tolerances and what are the standard tolerances? I've discussed that that the system there, like what you say, it is having 18 grades. So IT1, IT01, IT1, IT2 here. It is not one. It is two here. IT2 and so on till IT16. So there are 18. Okay, there is IT0 missing here. I did not write that. IT0. Okay, let me type that. It's good that I type it. It's not good here. Erase. So these are 18 standards that we have, but we use the tolerances only from IT5. Why it is IT5? Uh, I'll tell you because there is a reason behind it. Okay, fine. So I can say the standard which is obtained in terms of tolerance limit, that is I microns. So where I is given as where I is given as, there is a formula. You have to remember this formula for your examination point of view. That is I is 0.45 d to the power of 1 by 3, okay, plus 0.001 d. There are two zeros, right? R20 d. What is d? D is the geometric interference fit. Is not clear. What? Why it is not clear? What is the problem? You take any dimension of shaft, either lower upper. You take any dimension of hole, either lower upper. It won't. It's not going to fit. Shaft is not going to enter into the hole. That is what is this. What's the point? Yeah. So this is geometric mean of the lower and upper sizes of dimension step. So they're going to mention this dimension steps. Dimension step in dimension steps will be I mean, will be given in mm. So dimension d1 and d2 are already standards. It is geometric mean. It means that let's say if d1 is given, d2 is given, then d is equal to geometric mean, in the sense d1 and d2 under root is your geometric mean. Okay, fine. So what are the grades and what are the standard tolerances? So what I told that from IT5 only we are going to discuss that. So grade of, they say that like this is grade of manufacture. So let's say I'm writing this values here. So he says that the grade of manufacture is on the left hand side. On the right hand side, these are the standard tolerances that you have to put. Standard tolerance. So this is IT5, then standard tolerance is 7i, and if it is IT6, then the standard tolerance is 10i. I is what? I is this formula. I is this formula, and D is this formula. Okay, and IT7 is like 16i. IT8 is 25i. IT9 is 40i. So all these things sometimes is given in examination. IT16 is 1000i. So don't worry, everything will be given. So the what you say, the fundamental deviation, or whatever the, because the problem starts with the fundamental deviation. So the fundamental deviation is given, an empirical is given by an empirical formula. So let me write that also. Is it in the next slide? No, I'll write here. So let me write the fundamental deviation of empirical formula of fundamental deviation. So empirical empirical formula of fundamental deviation is like, is given by, it's given by some epsilon. Epsilon is some deviation, let us say. Then it is minus 5.5 d to the power of 0.74. So this formula might not be same for all the types given. So different shafts for different holes, the fundamental deviation will be differing, but it will be given an empirical formula. In examination, you can use this empirical formula and solve the problem by taking this thing. Okay, fine. So this is the grade and standard tolerances that you are putting, and this is your this thing. And IT 01 to 016, there are 18 grades for each. From 5 we are going to use. From 5 to 16, we have this standard tolerances given, and this is the fundamental deviations, empirical values. Okay. So you can see the specifications of the tolerancing. See, he says that whole, because why it is given a capital H, whole. Okay, let me write a different thing here. One minute. Okay, fine. So okay, H is given the and this 40 is what is, see the basic size here, and H represents the tolerance grade here, IT grade, and I mean H represents the what you say, the whether it is hole or whether it is a shaft, and also I told you there is a grade here. So if you see the diagram here, this is what is this H. It is representing that this is what is H. So from, it will start from A, B, C, D, E, F, G, H, I, J, K element and till Z, and it will start from A, B, C, D, so on, so till Z. See here, till H, till H, everything left to that is which fit, everything right to that is which fit, can you say? Can anyone say this? Left to that H is which fit and right to that is which fit? Left is clearance and right is interference. What about H? It is exact fit, no? You take the lower limit of shaft and higher limit of hole. So higher limit of shaft and lower limit of hole, it is exact fit. So this is what this H grade that they are trying to say. This is your H. That is what they are trying to say. And if it is given in capital, then it is hole. If it is given in small, then it is the shaft. Okay. Okay. Similarly, you can see here. 8 is the IT grade. IT grade 8 means IT 8. 8. It means that the standard tolerances that I have to put is 25i. Okay, and basic size shaft is this. Shaft is like it is 40, and F is a hole type, a shaft type, and then this 40 is basic size, and F is your IT grade. IT 7 you have to give standard tolerance of 16i. That's it. And fit is like your fit. What you are seeing is H8 and F7, and 40 is your basic size. That's it. Variety represents the international tolerance. Okay. Okay, let's try to solve this problem. Please, can you attempt this problem? It's telling us find out the limits and tolerances for 50H7, D8, and dimensions of steps are given. So D1 and D2 are also given. Then can you find what are the limits, upper limit and lower limit of hole here? Can anyone do this problem? And you can take all the formulas. I is 0. Uh, um, what do you say? Okay, I'll write all the formulas. You do this. You do this. Okay, I'll give you the basic size. And H is fundamental. H is having IT 7 here, and D here is having IT 8. Here 8 is it IT grade. 8 is IT grade. For IT 8 25 I is the tolerance that you have to keep. Fundamental deviation that you have to keep. And tolerance that you have to keep. And 7 is okay. Let me solve this problem so that we can do the next problem. So because it's not good that I tell you to solve the first one. Okay, fine. So basic size. What is given? Basic size is equal to 50. Okay. The fundamental deviation of hole H. Fundamental deviation of hole is uh, IT 7 grade. And so for IT 7 grade, it is 16 into I that you have to put. But we didn't calculate I. Let's calculate I after some time. After some time, it could. The fundamental deviation for shaft is this D, that is small d. Then it is 8 is given. So IT 8 and replies 25I. Okay. So the steps are given. This is D1 and this is D2. So let us calculate D. D is D1 and D2 geometrical mean of these two. So this is 30 into 50. So the geometrical, can anyone say what is the value of this thing? 30 into 50 under root. It is 38.72. Good. 38.72 mm. Okay. So I told you the formula as 0.45 d to the power of 1 by 3 plus 0.001 into d. This is your I formula. I is equal to, let me substitute the d value, 0.45 into 38.7 to the power of 1 by 3 plus 0.001 to the into 38.7. Can anyone say what is the value of I? Okay, it is 1.56 micrometers. Huh? Micrometers, what is it? Meters or micrometers? Actually, this will be giving the micrometers. Okay, this whatever I are calculating will be giving in micrometers. 1.6 or 1.56. Sorry, 1.56 micrometers. Because after substituting these values, you'll get in micrometers. So tolerance for hole you calculate. Tolerance for hole. Tolerance for hole That is, that is 16i, and that is 16 into 1.56, and that will be how much? Can you tell me how much is this? Tell me in not micrometers. Tell me in Then it is 0.24.96. Okay, let me write 24.96 micrometers. So it will be 0.02496 mm. This is your tolerance of hole, and tolerance of shaft. For shaft is equal to 25i, that is 25 into 1.56. Tell me how much is the value? 0.039 mm. Good. Okay. So the fundamental deviation for hole is denoted by h, which is like obviously the lower limit of the fundamental. Here we are assuming that it is a assuming to be a whole basis system. When I'm assuming like that, in examination he'll clearly mention. So if at all you are assuming a whole basis system, then the what is whole? For whole, what is the dimension? So limits for, can I write limits for whole? Limits for whole, can I write, if your lower limit of whole is 0, then how come I write it is 50, this is 0, and upper limit will be how much? Can anyone say? It is 0.02496 will be your upper limit, that is plus here. Okay, got the point? And as I'm considering this as a whole basis system, this is your whole, you got this as 0.02496, but shaft is somewhere here, so you have to have the fundamental deviation. So how do you calculate the fundamental deviation here? The fundamental deviation for the shaft is given as the, okay, this is not fundamental, this is standard tolerance. Sorry, this is standard tolerance. Standard tolerance, I also got confused. Standard, okay. Fundamental deviation is given by some empirical formula. So fundamental deviation for shaft. Okay, this page is, next page is different. Okay, let me copy this slide. Oh my God, it went. Oh, I erased all the things. Oh my God. Fine. Okay, fine. At least you got the point, no? So what I'm trying to say is that your fundamental deviation will be given. Actually, what happened is that he has taken the whole the system. You have calculated something 0.024 something something you calculated, and what is trying to calculate the dimensions of shaft. You know the whole dimension is 0 here, and he's trying to calculate this fundamental deviation. Then it will become the shaft here, and whatever the value you get here, and after that you add this value, whatever the tolerance that you got, no, the basic tolerance you got for hole, no, the for shaft, no, so you add that and you put it that here, that is what is this. Okay, fine. Anyways, so this dimension steps, I'll tell you, but by in the meanwhile you solve this problem. As I deleted all this, I'm not happy with this. Please try to solve this problem, then we can discuss what is this dimension of steps. Please try to solve this problem. Okay, come on, solve this problem. Coming. Anyone who got the answer? Okay, somebody got the answer. Mm, no, it is 0.002. Huh? Should be positive, no? For if you are considering whole, as the lower limit is 0, the upper limit should be positive value, right? It is how much? Can you tell me? Yes, excellent. Whole 30 to 30.012. Excellent, Abhishek. And shaft, please try to calculate shaft, Abhishek. You're talking about whole basis system, no? Abhishek is talking about, yeah, whole basis system. You're right. So tell me for the whole basis system, whole is 32 30.012. What about shaft? What are the values of shaft? I want shaft. Shaft in whole basis system. What are the dimensions of shaft? Uh, 27.972 to 20. Excellent. Very good. Very good. Very good. Very good. Very good. So fine. You Abhishek, you try to solve for the shaft based system, and I'll try to solve the whole based system onto the slide here. Excellent, Abhishek. Very good. So what is given? So first one is whole basis system. Okay. So if you are taking whole base system, you should take the diagram first. So let me take the diagram. Then this is your basic hole, and the shaft lies somewhere else. Okay, let's have hole and shaft have a basic size of 30. So obviously this is your 30. Okay, and he's saying that to have a clearance fit. Clearance fit in the sense, obviously shaft will be somewhere below here. This will be your shaft clearance fit. This is hole and this is shaft. Okay, fine. With a maximum clearance of 0.04 and minimum clearance of 0.2. So this is your minimum clearance. This is your minimum clearance, that is your 0.02, and maximum clearance I told you this is your 0.1. 0.04. Okay, right. So now, if this is 30 and minimum is 0.02, maximum 0.04, I told you, and the hole tolerance is to be 1.5 times the shaft tolerance. So he's saying that like the hole tolerance is 1.5 times the shaft tolerance. So what is the shaft tolerance? So to calculate the shaft tolerance or what the hole tolerance, then you have to see the technique here. So let us assume the shaft tolerance is X. Let us assume that shaft tolerance, whatever that you are trying to put here, is X, because uh, this is X, and he told that hole tolerance is 1.5 times X. 1.5 times X, right? So this is X plus 0.2 plus 1.5x will be equal to 0.04, because I'll write that equation here. So I'll come from bottom. X plus 0.02 plus 1.5x will give you 0.04. Then you can find out x. What is the value of x? Anyone? It is 0.008. So now you got the shaft tolerance, that is 0.08. So this x is 0.08. Let me write that here. X is 0.08. X is equal to 0.008, and this tolerance 1.5 times x is the what you say, 1.5 into 0.08 will be 0.012. So this tolerance here is 0.012. So now this is 30, this is 0.012. Let me write that value here. I don't want to write here. Let me write that value here. This value is 0.012. Okay, so now we got the dimensions of hole easily. So what is the dimension of hole? So for hole, you have the basic size of 30, right? And the maximum size, so the minimum size is 30 and the maximum size is 30. This is 0.012. So this is your for hole maximum size is equal to 30.012. Minimum size is equal to how much is that? 30. In the similarly shaft, from shaft already the upper limit is like 30 minus 0.02. So for shaft it is 30 minus 0. Okay, I like the limits. 30, the bottom will be 0.02, that is what you can reduce, right? And the upper limit will be 0.02 plus 0.008, that is at 0.028. So there is 0 plus 0.028, that is your shaft. No, it is both are minus, no? So let me write minus. Yeah, both are minus. So like maximum minimum size, wait. So maximum size of shaft is 30 minus 0.02, that is 29.98 mm. So everything is in mm. And minimum size of shaft is equal to 30 minus 0.02 minus 0.008. So this will be 29.972 mm. That is what the Abhishek got. It's right. Similarly, solve for the shaft based system. Did everyone got this problem? Only Abhishek is answering. Everyone? Anyone who did not get this point what I am discussing here? Guys? Okay, clear, good. So in shaft basis system, it's nothing but shaft basis system. So you start with this basic shaft like this. This is your shaft. Obviously there is a clearance, so hole will be somewhere here. So this is your 30, right? And also we told this is x and this is 1.5 times x. I already told you, and this is how much? The clearance is 0.02. So with this again you can calculate same thing. It will be, you can calculate the same equation, that is your x plus 0.2, 0.02 plus 1.5, so 0. So x will be 0.08 and this will be 0.08, and the dimension of this will be 0.012, and oh no, 0.012 only, right? Yes, it's 0.008, sorry, 008. This is 008. Okay, let me erase and write, should not get confusion. 008 and this is 0.008. Once you know the values, you can easily calculate the whole dimensions. So whole for maximum you can get as 30 point, I'm writing the answers here, 0.32 mm, and minimum as 30.02 mm, and for shaft maximum is 30.0 mm and minimum is 29.992 mm. The simple formula. Good. So please try to solve this problem. Okay, Abhishek has asked the step one, right? It is nothing but the steps are decided for each zone. Let's say if you're going this thing, right, like the uh, diameter D in steps, right? So for each grade there are different diameters. I'm not giving the table, that is standard table. So they say that like the tolerances lies in between that diameters. Okay, so that is fixed. So I didn't give the diameters. So they say this diameter is the geometric mean of the lower and upper diameters, and it is like for a diameter step within which the whatever the chosen diameter will be lying. Okay, so that is what is this. Okay, there's a table for that. I didn't write the table. Please try to solve this problem. So here given, he has given the steps, diameter step. that is 50 and 20. So the diameter you can calculate as under root 50 into 80. That is your how much is this? 50 into 80. According to the calculation, what I have, it is 63 point some 24. Yes, 63.246 mm, and the fundamental tolerances can be given as this 0.4. I mean, I can be given as this one 0.45. That is 1 plus 0.001 d. You can calculate this. That is I is equal to 0.45 into 63.246 to the power of 1 by 3 plus 0.001 into 63.246. So you can calculate I. What is the value of I here? Anyone in microns? Microns, and tell me in mm also. Okay, tell me in microns. 1.86 1.856 microns. Okay, 1.856 micrometers. Then you can convert this into mm. So for IT7, I told you that the fundamental, whatever the tolerance width will be 29. 16 into I is 29.69 microns as I calculated here, and this will be, oh sorry, I'm writing the answers because there's no time waste. Micro mm, and this will be 0.0296 mm, and for IT8 it is 25I, and if you calculate that, it is 46.4 micrometers, and that will be 0.046 mm. That is what the calculation that I have seen here. And he told that the fundamental deviation or upper deviation is given as this. So the epsilon is given for f means it is given for small letter means shaft. For shaft, the fundamental deviation for shaft is, let me write that, fundamental deviation for shaft, let me write that, f, he told that is minus 5.5 into d, that is 63.246 to the power of 0.41. For this calculation, it is like minus 0.03 mm. That is what is the fundamental deviation of the shaft. So it means that, like, if this is diagram, the shaft, this is your hole, and this is your shaft. So this is a hole based system, I think, right? Calculate the fundamental holes. Why? Yeah, H is mentioned. As H is mentioned, you can see it is a simple hole basis system, because if you see the diagram here, the H is directly coinciding it here. So as H is mentioned, then it is a hole basis system. Small h is mentioned, it is a shaft basis system. So capital H is mentioned, hole basis system. So if it is hole basis system, let me write the hole attached to the baseline. So this is this hole, this is the shaft, hole and shaft. So he told we got minus 0.03, so this is negative, that is 0.03 for shaft. From here you can calculate the hole maximum and minimum, shaft maximum and minimum. Can anyone tell me what is the hole maximum minimum, shaft maximum minimum? Hole max min. Hole is 64 to 64.046. Excellent. So max is 64.0464, right? And minimum is 64. And shaft, can anyone say shaft? Maximum and minimum? So this is width of tolerances we have already calculated for hole and shaft IT7 and IT8. So this is IT8, this is IT7. We have calculated that is 0.0296 IT7 and 0.046 is for IT8. Yeah, 63.96. What is 64 minus 0.00 64 minus 0.03, because this is what is this. I think whatever Abhishek, please check. 64 minus 0.03 is how much? 997. Abhishek, you may have made some mistake. Please see. Oh, you took oh, 0. Okay, fine. If you're taking accurately, it's fine. So if you take 0.03, it is the maximum value of shaft is 63.997, and 63.997 minus 0.0296. How much is that? 60.997 minus 0.0296. It is 63.9674. Okay, 63.9674 is the minimum value of the shaft, and it's telling to calculate the. Okay, everything has been calculated. Good, fine. Hope you understood the problems here. This is how these questions have been asked in previous year GATE also. And please take this question as assignment and solve this question. We'll discuss the solution tomorrow. Please take this question as assignment. Please take a snapshot of this thing as assignment, or else I'll be uploading the slides right away now. Please solve this question as an assignment in your room so that we can discuss tomorrow. As of now, I'm stopping the recording. We can discuss the angle measurements and linear measurements in the coming class.